Good afternoon. Hello, class. Good morning, good afternoon, whenever you're watching this. I do apologize for this video late to you. A lot of stuff is going on right now. So you will have an extension just because this lab when you can. The buffer lab shouldn't take you too long. I'll show you all the calculations you do. Even though all you have different data sets, most of your numbers are pretty much exactly the same. That being said, I have a different data set than all of you because I want you to fully copy my work. The data set I'm using as an example is data set A. This data set is basically going to do 95% of all the work for us. So, data set A, our system or our buffer system, how we prepare the buffer theoretically, 25 milliliters of that, 25 milliliters of that, gave it a pH of that. This right here is going to be part B. That's how a dilution affects a buffer. Right here, determining buffer capacity, how much a buffer can actually withstand. So, now we're going to talk about the lab. Here is buffer. So I already filled some of this stuff in already. Here's my buffer system, all right? Here is the weak acid of it, and here's the conjugate base. Now, the pKa has to be found in the lab manual. Look for all your things. Here mine is, right there. Now, this buffer range, pH range for buffer, what this basically means is this buffer system can handle pH changes between 6.96 to 7.21. Anything beyond that or lower than that, the buffer becomes completely useless for. So, next we talk about preparation of a buffer. So I gotta put these things right here, you actually can delete those or just put an A for all of those because you're only doing one buffer system. When this lab is normally run normally, we would do multiple, but now we're only gonna do one. Okay. Down here, preparation of a buffer. Volume, weak acid, volume, conjugate base, pH prepared buffer. The pH of the paired buffer is the 6.96. That's the pH given. And we're going to find the volume. And we're going to do that by using Henderson-Hasselbalch equation. Before I do that, I can actually already hear some of you in my head asking why that's the range. Well, if you Henderson-Hasselbalch equation where pH is equal to PE Ka plus log of A over HA. If you make A and HA equal something, that equals 1. The log of 1 is 0. Thus, your pH will equal pKa. Thus, your maximum pH for a buffer will be the pKa. Okay. Now let's talk about how to find volume. Again, I apologize. I'm still using my mouse to write. It's been impossible to send my computer off for about 2 weeks because I've been always busy. So we're going to have my bad handwriting again. I do apologize. So pH equals pKa plus the log of A over HA. Now we're going to use this right here, and we're going to solve for it. So first things first, we're going to minus pKa. Well, not that part. And then bring it down step by step. Our pH minus pKa is equal to log of A over HA. Base 10, base 10, cancel, boom. So now A over HA is equal to 10 of pH minus pKa. Now, what do? You just plug in our values. So, green, 6.96, 7.21. They'll give you 10 minus 2.5. Plug into your calculator, you get 0.563. So A over HA is equal to 0.563. Now, we're not done yet because that's going to be our total concentration. We got to figure out what the volumes are. So this is kind of weird. I'm going to solve for HA first. And HA is going to be equal to the concentration of the buffer, 0.1, which was found in the buffer system. It's always going to be 0.1 over 1, because it's A over HA, one going to do the exact same thing, plus the total we just calculated, 0.563. So when you do this, you get 0.64, and that's going to be the concentration for HA. Now, we're going to take that and subtract it from this. Now, you're probably asking why that and not this. Well, this is going to be the total of them put together. I want the buffer one. Because when you add those together, the concentrations will be a bit different because you're changing it because of volume. This is the one I'm looking for right here. Because remember, M1V1 equals M2V2. You add two things together, it changes the concentration. So this was the concentration of them together. This is going to be a modified one right here of our buffer. Now, let's change colors so we don't confuse you guys. Let's do hot pink. 0.1 minus 0. Oops. 0.064. And I got 0.0364 my A, HA. But these are in concentrations, which is moles per liter. So we're going to convert those. Now the total volume is going to be 25 plus 25 or 50. That can also be found in the buffer system. I'll show you that in a little bit. But right now, let's keep on going. 5 liters, 0.05 liters. Okay. So here will be 0.003. 0.0018. Now, moles, 1 over 0.2, 1 over 0.2, and that will give us for HA and A. For HA, we'll get 0.16. Oops, did I hit it correctly? Yes, I did. And then for the one, we'll get 0.009. These are milliliters. You can keep them the same or convert them into liters, and bada bing, bada boom. All done. So that's where you're gonna put you put the liters formed into here and here, and that's what you get there. Now for this part, it is simply, let me see if I can split my screen. Cool. You're simply just gonna put the volume. So for that concentration and this concentration, So 6.85, 6.86, and volume buffer. 1 second, I misspoke, and I have to fix something real quick. Okay, I'm back. Sorry about that. I had to take care of something. So there you go. There is your pHs for those buffers. Boom, boom. What's going to happen here is you need to do M1 V1 M2 V2. Now, you only need to do calculations for one of them, but it's the same thing. So I should do the calculations for this guy right here. VM1 V1 equals M2 V2. Now we're solving for volume, which means boom, M1. So V1 is equal to the concentration 0.05 times the volume. This guy would be 5 milliliters divided by the concentration of 0.1 gives you a volume of 2.5. So you put 2.5 here and do the exact same setup, except these numbers right here will change to represent this guy. Okay. Boom, boom, boom. Next on to this trial right here. So initial pH, 6.89, 6.91, 6.94. Whoops. Final pH, 8.02, 7.93, and 7.86. The volume is going to be that. Let's change it to liters real quick. That way we can do some calculations a bit easier. So 0.000, oops, 0.95. And then we have so buffer capacity is going to be the number of moles over change in pH over the volume of in the buffer. So what this basically means is you're going to do the change in pH, so final minus initial. That goes right there. The volume is just going to be this guy right here. And then number of moles. Now, NaOH is a strong base, which means it's associated 100%, which means the concentration of my OH molecules is also 0.1, which is also just moles over liters. So if I do this, I can multiply that by 0.0, boom, boom, cancel, cancel. And right there will give you the number of moles. That equal buffer capacity, put that here, here, and here. Add those up, divide by the amount, and you get the average buffer capacity. And that's pretty much all the calculations you need for this entire lab. And let's go to the post-lab questions. In your own words, what is a buffer and what does it do? You guys should know this. How does your pH buffer, prepared buffer, compare it to a desired value? How does this number, the 6.96, compare to the 7.21? Number 3, can solutions than those utilized in the experiment you can use for the reference? This one right here is a free game one. Try your best to explain it. I'm just going to give you points if you put anything, but please try. It's really an interesting way of looking at it. And basically, can you use other things besides the things in your buffer to make similar pH range for your buffer? Yes or no? Was the change in pH immediate or not? So if I have a buffer and if I add a strong acid or a strong base, the change in pH will be immediate. It just won't be a lot, but the pH will change immediately because the strong acid, strong base will dissociate 100%, attacking the buffer immediately. There is no little reaction that had occurred. It's an immediate reaction. It's just a gradual change because a buffer resists the change in pH. How will the buffering capacity of a solution change if you increase the concentration of acid or base? Well, this should make sense. If I have a base and I increase concentration, it becomes stronger. A stronger base can kill an acid, so it can kill a buffer much easier than a weaker base can, and vice versa. Does that make sense? Put something like that in there. For my engineering students, try your best. This is more of a biology type of question. But bicarbonate, urea, lungs, the kidney, that type of thing occurs in the body. Do a little bit, put anything, you'll get points. This right here, you gotta tell me which one of these people will be hired based on their answers. So, is it a strong acid or weak acid? Strong acid or weak base? Sorry, strong or weak acid, strong or weak base. What makes a buffer? Same thing there. Same thing there. This one just tells you in words. Hint, hint, wink, wink. This one, look up the pKa value and see if it's close to 9. If it is, they're correct. If not, they're wrong. And that's pretty much this. Shouldn't take you too long. Most of the work is pretty much exactly the same as mine, but there you go. I'll stop my sharing. Hopefully it was helpful. Please get this to me as soon as you can. I do apologize for making the video so late, but there you go.